this video, we're going to talk about radical expressions, rationalizing denominators, and I hope you don't mind my voice is a little bit more like Barry White today. I have a slight cold. It is that time of year, so anyhow, you'll just have to bear with it while I go through this lecture. Anyhow, prerequisites for rationalizing denominators is simplifying radicals. You have to know pretty much everything about radicals, multiplying them, and that type of thing. And also, as I introduced in the last lecture, which is the advanced topics for radical expressions, I introduced the idea of a conjugate. I'll also reintroduce that here very quickly, and then we'll get into the idea of rationalizing denominators. Now, before I begin, I want to say that generally, I do not force my students to rationalize denominators. This is kind of a throwback to an old process, and I'll show you that process in just one moment. First, let's start with the basic question: what is rationalizing denominator? What does it mean when somebody asks you to rationalize a denominator? Well, it has something to do with a denominator. Specifically, like you could have a fraction where you might have the square root of 7 on the bottom. Or you might have a fraction where you have x over the square root of 3 plus x. Or you might have a denominator where you have 5 over the cubed root of, let's say, 4 plus 1. Something like that. And it could get worse, obviously, but the idea is that you see in each of these denominators there's radicals. And it's been a tradition in mathematics that we don't want radicals in the denominator. Now, I say it's a tradition in mathematics because in reality there's no reason to do it anymore. But some teachers still force it upon their students. If you have an instructor that forces it upon your student or forces it upon you, you can have them watch this video because I'll explain why, the only reason why we pretty much rationalize denominators. Now, it's a good skill to have for future courses. Just like completing the square. I don't use completing the square to graph a quadratic equation. However, it's a good skill to have to graph circles. And rationalizing denominators, while it's not really a great skill to have at this point, in future courses, actually, in a calculus course, it becomes kind of a handy tool to have. So I'm going to take a single example of these three here. I'm going to look at the simplest one. The process to get that square root of 7 out of the denominator is actually easier to see if you work with rational exponents. So square root of 7 is the same thing as 7 to the 1/2. When you say that, you kind of realize, wait a second, that's the half power of 7. And I don't want any half powers in the denominator. I want full powers only. So what you can do is you can multiply this fraction by 1. But I'm going to multiply it by a special version of 1. 1 in the form of 7 to the 1/2 under 7 to the 1/2. You see, 7 to the 1/2 over 7 to the 1/2 is 1, so I'm not really going to change this fraction other than the look of it. And the reason why I chose 7 to the 1/2 is because I have a half power. I want to make it a full power, so I'm going to tack on another half power. A half power plus another half power becomes a full power. And so this will then become 3 times 7 to the 1/2 over 7 to the 1st. Or in other words, 3 times the square root of 7 over 7. And this is basically how we rationalize denominators, is that we look at the denominator itself and think, okay, let's see, I have a radical there, and the radical is a half power in this case, so I'm going to somehow multiply it by some form of the half power of 7 as well. Just like in the second example here, I'll want to multiply that denominator and the numerator by some half power of 3, but it's going to be a version of the half power of 3. This is going to be a very special version. So I'm not going to talk about it yet. So let me get into the why this is a traditional approach first, and then I'll go into how you do these last two. So here's a good question. Why do we rationalize the denominator? Let's take a simple example. 1 over the square root of 2. It's a very popular fraction, actually, in trigonometry. If you take a look at this fraction, let's suppose that we don't have calculators available to us. Let's just suppose that we live in a world where there's no calculators, which was a world not too many years ago, not too many decades ago, maybe I should say. And what they did at that point is they referred to these books of tables, basically. And in these books of tables, they had a table for the square. They had a approximation for the square root of 2, an approximation for the square root of 3, an approximation for the square root of 5, and so on and so forth. So they had all these approximations built into these tables because you didn't have calculators. So if they wanted to find out what 1 over the square root of 2 is, they would refer to the table and they would say, okay, I need to know how many times square root of 2 divides into 1. And so they would do this long division because they didn't have calculators. Now let's suppose I just looked this up in a table. Square root of 2, their approximation, let's say, is 1.414213,562. And I want to know how many times that goes into the number 1. Well, that's a pain using long division because then we have to move over this decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. So let's suppose we do that. And now I just want to know how many times does this number, the divisor here, go in to the dividend. And as you look at that, you know that's going to be a mess. I mean, that's going to be a mess. First of all, it doesn't go into this number. We'd have to put another 0 here, and it goes into this number, actually 7 times. But it's hard for, I mean, obviously, if you're doing this by hand, that's going to be a horrible, horrible calculation. So, some genius came along and said, listen, I know that since we don't have these fancy-dancy calculators, they didn't say that, but whatever, this computation right here with this simple-looking fraction is going to be horrible. So why don't we change the form of this fraction, turn it into an equivalent fraction, by multiplying numerator and denominator by the half power of 2. If you multiply the numerator and denominator by the half power of 2, well, the numerator becomes a half power of 2. Okay, but the denominator becomes just regular old 2. And look how easy this division is. How many times does 2 go into 1.414213,562? The decimal place there. 2 doesn't go into 1, but sure does go into 14 7 times. Subtract, right? Carry down the 1. 2 doesn't go into 1, but it goes into 14 7 times, and you can keep going. I already have 3 digits of accuracy. So that's pretty fast, and that's why rationalizing the denominator exists. Because way back when they didn't have calculators. Well, now we do. So what's the point? What is the point? There's no real point to it now. Not at this level. One last thing before we get into how to do these officially. I want to reintroduce the definition of the conjugate. A plus B is a conjugate of A minus B, and A minus B is a conjugate of A plus B. We'll use that concept in just a moment. Now let's start with this one. This fraction has a radical in the denominator, so what I'm going to do is multiply top and bottom by the half power of 12 to make that denominator have a full power of 12. Here we go. We get x times the square root of 12 on top, and on the bottom we get a full power of 12. Remember, you should always simplify your answers, so in the numerator, the square root of 12 is the same thing as square root of 4 times the square root of 3, and the square root of 4 is the same thing as 2, so we have 2x root 3 over 12, or in other words, x root 3 over 6. And that is the simplified form of that first fraction with a rationalized denominator. How about the square root of the fraction 2a over b? Now, if you recall when we talked about simplifying radicals, and I think I might have that definition back here. Yeah, I do. I had several steps for simplified radical. First thing, each factor in a radicand is to a power that is less than the index of the radical. So when you look at the radicand, all the powers on the inside have to be lower than the index. The second thing is a radicand cannot contain any fractions. In our current example, it does. Third thing, and I have this grayed out, is because I don't really adhere to it, but all denominators must be rationalized. And then finally, each term contains only one radical. So in other words, you do not have the square root or cube root of x times the cube root of y. You glue them together. But the issue with this one is that we have a fraction underneath the radical. So we're going to split that fraction, square root of 2a over the square root of b. Now, I'm going to go ahead and multiply numerator and denominator by the half power of b. So square root of b against the bottom, square root of b against the top. You have to do it to both top and bottom because that makes it to where you're multiplying by 1. If you only multiply the bottom, you'd be changing the fraction. So let's see, we multiply these two together. In the numerator, you get the square root of 2ab. In the denominator, you get just a beautiful little b. There is a little note I should put on here. We're going to assume that all variables are positive. And there is a reason why you'll see in the next lecture. It's generally the last topic that people talk about when they talk about square roots and powers of radicals. So we have another example. 2 times the square root of 3 divided by the square root of 2k. Again, I see the denominator contains a half power of a picture, that picture being 2k. So I'm going to multiply the denominator by the square root of 2k and the numerator by the square root of 2k. When you do that, the numerator becomes 2 times the square root of, remember, square root of 3 times the square root of 2k is the square root of 6k, all over 2k. 2's will cancel. This will be the square root of 6k over k. And no, the k's do not cancel. Don't do that. That k in the numerator is locked inside that square root. You cannot cancel the k's. And then all of a sudden, we get into an example where we have x over y minus square root of 2. Notice there's two terms in that denominator. So multiplying by just a power of 2, in other words, 2 to the 1/2 power or the square root of 2, while it will make this square root of 2 turn into a regular old 2, it will also attach another square root of 2 over on this y. And let me just show you that kind of quickly here. If I multiply top and bottom by root 2, I'll get x times root 2 in the top. In the bottom, I'll get root 2 times y minus 2. And notice that I still have a radical in the denominator. And if I multiply top and bottom by the square root of 2 again, so if I think, oh, well, maybe I have to multiply it again because that'll get rid of it, I'll find out the top becomes 2x and the bottom becomes 2y minus 2 root 2. And again, I still have a radical. So this is obviously not working for me. So the question is, what do we do? What do we multiply that denominator by to get rid of all types of the radical? Well, the idea is to multiply it by its conjugate, y plus the square root of 2. The reason why is not so apparent at first. Actually, maybe it can be apparent. If you think about the way back in the day when we were doing factorizations, we came across a difference of squares. So x minus y times x plus y became x squared minus y squared. And actually, maybe I should write that down. So recall that x minus y times x plus y became x squared minus y squared. In this case, it's y minus root 2 times y plus root 2, so this should turn into y squared minus the square root of 2 squared. Notice what happens when you square the square root of 2. The radical disappears. The numerator I'm just going to write as x times the quantity y plus the square root of 2 for now. So this becomes x times the quantity y plus the square root of 2 all over y squared minus 2. And notice that our denominator no longer has a radical in it. So the rule of thumb here is to multiply both top and bottom by the conjugate of the denominator. Now some people will say that this is not finished, that I have to distribute the x. You could do that if you want. That's an acceptable version of the answer. I generally do not like to do that because we've been taught for so long to factor, factor, factor. So why do I want to distribute? But both answers are absolutely acceptable. So let's try this example. Now I notice that this denominator has two terms, so I know it's going to be that I'm going to have to multiply by a conjugate. It's two terms and a radical. So I'm going to multiply it by its conjugate, which is 3 plus the square root of 5. I'll attach that to both numerator and denominator. When you do this, please use parentheses so it convinces you that you have to do distribution here. I'll do the distribution slowly so that you can kind of see what's going on. In the numerator, I have root 5 times 3, or 3 root 5. Root 5 times a positive root 5, which is a positive 5. A negative 2 times positive 3 is a negative 6. And a negative 2 times root 5 is a negative 2 root 5. In the denominator, I have 3 times 3, which is 9. I have 3 times positive root 5, which is a positive 3 root 5. And then I have, sorry, I was going to say in denominator, a negative root 5 times 3, which is a negative 3 root 5. And finally, a negative root 5 times a positive root 5, which is a negative 5. Let's see how this simplifies down. In the numerator, I have 5 minus 6, that's a negative 1. And then 3 of these root 5s minus 2 of the same pictures. So 3 of them minus 2 of them, well, that'll give me 1 of them. It's just a positive 1 of those root 5s. In the denominator, I have 9 minus 5, which is 4. And then these two cancel out nicely. So this is the simplified version, or the rationalized, version of that fraction with a rationalized denominator. Now, as a final example, I want to take just some little bit of your time to talk about what if your radical is not the square root, but something different, like the fourth root or third root or fifth root or whatever it is. Well, the process, the idea behind it's still the same. I personally like to write these with rational exponents, 27x to the 1 over 4 power. And always remember, you want to make that a full power. Well, I only have 1/4 of a power on there, so I'm going to multiply this by that picture, which is 27x, to the 3/4 power. 3/4 power plus a 1/4 power will give me a full power. Whenever I do the bottom, though, I got to do the top. So this will be 27x to the 3/4 power upstairs. And when you multiply these through, I forgot to write an equal sign, sorry about that. When you multiply these through, you'll get on the bottom 27x to the first power, and on the top you have 9x cubed, and then you have the fourth root of 27x being cubed. And of course, there's a lot of other ways you could write this. Probably, well, you could probably leave it like that. I would clean it up to where at least that numerator, maybe I'll bring that power of 3 on the inside instead of having it on the outside. So we'll have the fourth root of 27 cubed times x cubed all over 27x. Oh, this can simplify. 9 goes into 27 3 times, and x goes into x cubed, x squared times. This will be x squared times the fourth root of some horrible number to the third power, x to the third power, all over, let's see, 9 goes into 27 3 times. Now, looking at this, you might think you don't want to do 27 cubed because it's too much work, but you actually can simplify that down. I don't know if you realize it, but 27 is the same thing as 3 being cubed. And of course, you're cubing that. So it does get a little messy, but you see that's 3 to the ninth power. Oops, that was the fourth root. So this will be x squared times the fourth root of 3 to the ninth power times x cubed all over 3. And now we're going to just do that idea here that 4 goes into 9 twice with a remainder of 1. So in other words, that this simplifies into, let's see, x squared, 3 squared is the fourth root of 3 to the first, x to the third, all over 3. And now we can do one last simplification. That's x squared times 3 times the fourth root of 3x cubed all over 3, or no, not all over 3. What am I talking about? We just cancel that. So there we go. That would be the final answer. Just to remind you kind of how I did this, you really want to write the radicands as prime factors raised to powers so you can figure out, well, how many times does this fourth root go into that power of 9? So 4 goes into 9 twice. So I have 3 to the 2 power on the outside. With remainder 1. So I have 3 to the 1 power on the inside still. That's how I got that.